There are 48 hours in October 2025 that everyone just has to shrug about. 2 days gone. Every telescope on Earth dead to the sky. The most watched object in the solar system swallowed up behind this wall of blinding light, and when it came back, it wasn't the same. 3IATLAS slipped out from behind the sun, changed. The scientists who caught it first, they're not talking about what they think happened. Picture it, 3 in the morning at Mauna Kea, way up at 14,000 feet where the air bites through every layer you've got. Dr. Sarah Chen sits hunched in the control room, face washed in the glow of monitors spitting out endless rows of data. Most people would never make sense of those numbers, but she's been living with them for 6 weeks, tracking 3IATLAS, working with teams around the world, building a trajectory model more precise than anything before. She knows where that comet is, down to a few hundred kilometers across billions of miles. She knows how fast it's moving, how it spins, every little drift. She thinks she's got its path nailed. Then October 29th rolls around. Everything cuts to black, not because something broke, but because the sun muscles right between Earth and the comet. The view fills with radiation that would cook her sensors if she even tried to look. You've probably heard about 3IATLAS, the interstellar comet that showed up in our solar system in the middle of 2025 and instantly stole the spotlight. NASA called it fascinating. The news called it historic. All over the world, amateur astronomers couldn't set up their telescopes fast enough, hoping for a glimpse of this traveler from another star. But there's something nobody really talks about, something that never made it into the press briefings or the official statements. What happened during solar conjunction? That short stretch in late October when Earth, the Sun, and 3IATLAS lined up just right, making it impossible for anyone to see the comet at all. For 2 days, we were flying blind. And when we finally got our eyes back on it, the numbers didn't quite match up. The difference? It's subtle. Unless you spend your life crunching orbital equations and tracking down velocity shifts the size of a slow walk, you wouldn't notice anything at all. The comet still looks like a comet. It's got the same fuzzy coma, a little shroud of gas and dust wrapped around a solid core. The tail is still there, faint but visible, streaming out behind it in the sunlight. Spectrometers pick up the usual suspects: carbon dioxide, water vapor, all those classic signatures of ice boiling away in space. On the surface, 3IATLAS acts exactly the way you'd expect any interstellar comet to act after a close pass by the sun. But the math doesn't care about appearances. The numbers we got after conjunction don't line up with the ones from before. The difference isn't huge, just 0.03 astronomical units if you project it out for a few months. But it's not random either. It's not just noise in the data. It's a nudge, a correction, a tiny tweak in its path that seems to point straight toward a specific spot, Jupiter's Hill sphere. That's the zone around Jupiter where its gravity takes over from the sun's, a kind of cosmic parking lot where objects can hang out for ages without drifting away. If you wanted to stick around and watch the inner solar system, that's where you'd go. And that's the detail that keeps people up at night. This isn't really a story about what we saw. It's about what we missed and what might have happened while we weren't looking. Because in those 48 hours, 3IATLAS did something. The numbers said it would follow one path. After conjunction, it was on another. Not by much, but enough. You can measure it. It's real. And it's the kind of thing that makes some experts squirm. Just think about what it means to lose sight of something barreling through your backyard at tens of thousands of miles an hour. In normal life, you watch a car go by, and even if you blink or look away, you just know it's still following the rules. But space, out there, all you have are photons, little packets of light that have to cross millions of miles before they tell you anything. Miss a few, break that chain for even a short time, and suddenly you're guessing. You're left trusting your equations, your models, your grasp of how gravity works. You have to hope nothing weird happened when you weren't watching. Usually, that trust pays off. The moon doesn't just scoot away during an eclipse. Mars never takes a detour when it slips behind the sun. Gravity's laws are steady, reliable. You can work out where something will be just by knowing where it was. Unless something dramatic happens, that's where you'll find it. But comets are a whole different animal. They're unpredictable, both in personality and in physics. Made of ancient ice and rock, leftovers from the birth of solar systems, and when they get close to a star, they start to fall apart. There's no liquid phase. The ice just jumps straight to gas and drags dust with it, making that familiar coma and tail. But here's the kicker. All that gas escaping acts like a little rocket, pushing the comet, nudging it off its predicted path in ways gravity alone can't explain. This is old news for physicists. We've known for ages that comets don't just drift along, pulled only by gravity. Back in the 1800s, astronomers noticed something odd about Comet K. Every time it whipped around the sun, it showed up just a bit early. The cause? Not some cosmic mystery, just jets of gas shooting out from its surface, like a bunch of tiny rocket engines. As the comet spins, different spots heat up, gas erupts, and the whole thing gets nudged off course. It's messy, unpredictable in the details, but overall we get it. We can plug the numbers into our models, adjust our charts, and most of the time we know where a comet's headed. But not this time. 3IATLAS isn't your garden variety comet. It's an interstellar wanderer, a visitor from another star, flung out of its original system billions of years ago. It's been drifting through the cold, battered by cosmic rays and interstellar dust, exposed to who knows what out there in the dark between stars. Its makeup is strange. Its structure might be nothing like what we're used to. Even the way it reacts to sunlight could be totally different. And when we really dig into its path, the numbers start to get weird. There are tweaks and nudges that don't fit the usual outgassing story. Now, here's where things get interesting. There's this 48-hour window, right when the comet was closest to the sun, where we lost track of it. Not just any gap, but the exact stretch when everything should have been happening. Maximum heat, wildest outgassing, biggest orbital changes. If you were trying to slip by unnoticed, you couldn't pick a better time. That's what makes people uneasy. Maybe it's just a coincidence, just bad luck. But sometimes, coincidences stack up in ways that feel more like intent. Stick with me because this isn't some wild theory. We're talking hard data, thousands of observations, dozens of telescopes, scientists all over the planet, and they all point to the same conclusion. Something gave 3IATLAS a shove during those missing hours. Either it somehow managed the most precisely timed outgassing we've ever seen, just the right direction, just the right moment, steering itself toward a narrow gravitational target millions of miles away, or there's something else going on. Something that feels, well, intentional, like it was meant to happen out of sight. Look, I know deliberate is a loaded word. In astronomy, we're taught to steer clear of it. Space rocks aren't plotting, they move because physics tells them to. Gravity, sunlight, magnetic fields, that's it. No choices, no plans. But when the data keeps lining up just right, when the timing always seems perfect, when changes in the comet's path start looking like they were optimized for some outcome, that word, deliberate, slips into private conversations. It pops up in late-night emails, whispered at conferences, then quietly erased from official papers because no one wants to sound like they've lost their grip. But what if it's not just us projecting? What if something, or someone, built this thing to act exactly like a comet, to blend in so well we'd never notice unless we look this closely? That's the question that sticks with you when you're sitting in the quiet, waiting for another batch of data, watching the telescope crawl across the sky. It's not the kind of question you ask out loud. Most scientists don't want to touch it, not unless the evidence is so overwhelming it forces everyone to rethink what's possible. Occam's razor still wins out. It's just a weird comet, acting a little weirder than usual. For now, that's the easiest answer. It's funny how we throw around the word simple without thinking about what it actually means. People like to say natural explanations are simpler, but sometimes that stretch for simple starts to look a bit forced. If you have to line up a whole bunch of unlikely events, coincidences stacking on coincidences, just to make the natural explanation work, isn't that just as complicated as the alternative? At some point, you have to ask if we're piling on more assumptions than we're really comfortable with. Let's back up for a second and talk about what solar conjunction actually is, because the geometry is kind of the whole point here. Without it, none of this matters, especially when we're talking about 3IATLAS and why this particular window is such a big deal. Picture the solar system from above. Imagine all the planets laid out on a giant clock, each sweeping around at its own pace. Earth's path is our yardstick, one astronomical unit, about 93 million miles from the Sun, one lap every year. Mars is a bit farther out, at about 1.5 times that distance. Jupiter's way out there at 5.2. The gaps get crazy fast. Each planet is like an island, separated from the next by these huge stretches of emptiness. Now, 3IATLAS isn't playing by the same rules as the planets. While they stick to neat, almost flat circles, this comet is barreling through on a wild path, tilted about 30 degrees off the usual plane. It's coming in from interstellar space, diving toward the Sun, swinging around in a hard curve, and then shooting back out into the dark. It's set to reach its closest approach, perihelion, on October 30, 2025. With these kinds of orbits, there's always a moment when Earth, the Sun, and the comet nearly line up. It's never perfect. Space isn't a two-dimensional board, but close enough that from here, 3IATLAS will slip right behind the Sun. Think about standing outside, squinting at something that's smack in line with the Sun. Even if you block the direct sunlight with your hand, the glare is brutal. Your eyes water. You can't see a thing. Now, imagine that multiplied by 100. The Sun takes up about half a degree in the sky, just the size of your thumbnail at arm's length, but it's so blindingly bright that even a quick glance can wreck your eyesight. Telescopes have it even worse. They're built to catch as much light as possible, so if you point one at the Sun without a filter, you'll fry the sensors, melt parts, and ruin gear that costs a fortune. This is what solar conjunction does. It forces your hand. When the Sun sits between you and whatever you want to observe, you just have to give up. No amount of wishful thinking changes the physics. The Sun's glare washes out optical images. Its electromagnetic noise drowns out radio signals. Space telescopes can't look that way without risking real damage, and ground-based ones have the extra headache of our atmosphere scattering sunlight everywhere, turning the whole sky into a blue haze. For a short time, sometimes a few hours, maybe a few days, depending on how close things line up, you can't see your target. It's still out there, but the Sun blocks everything. Astronomers saw the conjunction window for 3IATLAS coming from a mile away. They worked out the timing months ahead, knew exactly when the comet would slip behind the Sun, and planned for it. Observation schedules got packed tight before perihelion. Every telescope pointed skyward, squeezing out as much data as possible before the blackout hit. The level of coordination went global, real teamwork, the sort that only happens when something big is on the line. When the Sun rose over Mauna Kea and blocked their view, telescopes in Chile picked up the baton. As Chile lost sight, Australia jumped in. It was a relay, one observatory after another, each handing off to the next, piecing together a full picture of 3IATLAS as it closed in on the Sun. That's just how it goes. Science knows how to deal with gaps like this. You work around them. You load up on data before and after, and in between, you trust the models, the ones astronomers have polished over centuries. These aren't shaky guesses. The math goes back to Newton, then gets layered with tweaks and improvements from every generation since. Perturbation theory, computers running detailed simulations, modern astrometry measuring positions down to a milliarcsecond. It all adds up. With all that, you usually know what happens even when you can't see it. But this time the models didn't fit the data, not with 3IATLAS. Solar conjunction isn't rare. Planets, probes, comets, they all run into it. Mars does it every couple of years. The Parker Solar Probe goes through it regularly. It's a known headache. During conjunction, the Sun drowns out radio signals and blinds optical telescopes. You can't look directly at it, not from Earth or space, without risking your instrument. For a while, sometimes hours, sometimes days, the thing you're watching vanishes. So astronomers did what they always do. They calculated the window early, packed in observations ahead of time, and lined up follow-up plans for when the comet reappeared. That's the drill. And you trust your orbital models to fill in the blanks. Except this time, those models flopped. 3IATLAS didn't behave the way they said it would. In the run-up to conjunction, 3IATLAS was under a microscope. The attention level matched what comet ISON got back in 2013, or comet NEOWISC in 2020. But this comet was different. It wasn't just another icy wanderer making a regular swing past the sun. 3IATLAS came from another star. That made it special, maybe the only one of its kind we'd catch up close in our lifetimes. That's why everyone watched it so closely. The Hubble Space Telescope keeps going, decades after liftoff, with its aging gyros and the occasional hiccup when an instrument fails. Still, it managed to snap some crisp images of the comet's coma and nucleus during a few observation windows in September and early October. Getting those sessions took serious planning. Every slot on Hubble's schedule is a battle, comets fighting for time against galaxies, exoplanets, supernovae, you name it. When the images came in, they showed a hazy, round coma about 10,000 kilometers wide, wrapped around a bright pinpoint, the nucleus itself. Figuring out how big that nucleus actually is wasn't easy. It's hidden behind a cloud of glowing gas and dust, and even with careful photometry, all you get is a rough guess, somewhere between 400 meters and 5 kilometers across. That's a massive range, the difference between a big office tower and a small mountain. But separating the light from the solid core and the light bouncing off the coma is tricky work. You have to make some tough calls about albedo, what it's made of, and how thick the dust is, and none of that's easy to nail down without flying a probe right up to it. Then there's the James Webb Space Telescope, top of the line for infrared. In mid-October, JWST swung its mirrors toward 3IATLAS for a round of spectroscopic studies to figure out the comet's chemical makeup. Infrared light slices through dust better than visible, so JWST could peer deeper into the coma and spot molecules you'd never see with regular telescopes. The data came back loaded with carbon dioxide, way more than water vapor, which usually wins out in comets from our solar system. The CO2 to water ratio put 3IATLAS way out on the edge compared to anything local. Not just CO2 either. The spectra picked up carbon monoxide, carbonyl sulfide, a dash of methane, and even some complex organics. These are the kinds of molecules that, given the right conditions, could start the chemistry that leads to life. Meanwhile, the big ground-based observatories joined in. The Atacama Large Millimeter Array in Chile, 66 radio dishes working together, picked up millimeter emissions from carbon monoxide gas. That told astronomers the comet was already venting gas, even though it was still far enough from the sun that you wouldn't expect much action. Early outgassing like this is odd, but not unheard of. Some comets wake up long before crossing the frost line, where different ices start to boil off. Maybe 3IATLAS has veins of supervolatile ices that vaporize at barely above absolute zero temperatures. Maybe its surface is weirdly shaped, focusing sunlight into hot spots that trigger early sublimation. Or maybe there's some hidden heat source inside, though no one really knows what that could be. From Chile to Hawaii, Australia to South Africa, telescopes track the comet night after night. Astrometry, the art of charting an object's spot in the sky, has gotten incredibly precise over the years. Modern detectors snap photos packed with thousands of background stars alongside the target. Software compares those star patterns to giant catalogs, billions of stars. All mapped out, so you always know exactly where you're looking. Stack up images from different nights and you can trace the comet's path against the backdrop of stars. Fit an orbit to that path, ellipse for something bound, hyperbola if it's flying through, and suddenly you can predict where it'll be in the future. Get enough data, and your uncertainty shrinks to almost nothing. By the middle of October, astronomers had the orbit for 3IATLAS nailed down. The ephemeris, the chart of where the comet would show up in the sky, had uncertainties of just a few thousand kilometers, even months out. Sounds big, but in the vastness of the solar system, that's pinpoint accuracy. If you wanted to send a spacecraft to meet the comet, you could plot a course and count on hitting your target. Astrometry had the comet's position and velocity locked in, with hardly any room for surprises. Or so everyone figured. Out of all the astronomers tracking 3IATLAS, a handful took detail to another level. They wouldn't just check their work once, they'd circle back 3 more times, looking for anything they might have missed. Dr. Sarah Chen at Mauna Kea was in that group. She'd been in the comet game for 15 years, ever since her grad school days digging into the infamous split-pea nucleus of comet Schwarzmann-Wachmann 3. That one shattered right in front of everyone, a big messy breakup that convinced her comets don't follow rules. So when 3IATLAS showed up, Sarah knew right away this could be her big break. She went all in, working so hard her coworkers started to worry. 70-hour weeks, normal sleep, optional coffee, essential, almost a meal in itself. But all that effort paid off. Her team's data from Keck was razor sharp, easily among the best in the world. Their numbers helped tighten up the comet's orbit more than anyone else. Every clear night, Sarah was there, sometimes in the control room, sometimes dialing in from home if she couldn't make the drive. After a while, she developed a gut sense for the comet. She could tell how it moved, how its brightness shifted, how the coma changed as it got closer to the sun. She'd glance at a raw image and spot tiny oddities others missed, little tweaks in shape or brightness that hinted something weird was happening inside. Just before conjunction, Sarah caught something strange. The comet was getting brighter, which made sense as it got closer to the sun, but the speed of that brightening was off. Usually, comet brightness ramps up following a power law, something like intensity equals distance to the sun raised to a negative exponent. Most comets land somewhere between -2 and -4. 3IATLAS was closer to -5. That meant either it was reflecting more light than people guessed, or something inside was firing up activity faster than expected. She made a note in the logs, scribbled a reminder in her research files, but didn't sound any alarms. Comets are unpredictable. That's just what they do. Maybe this one's chemistry meant it kicked into gear faster than water-ice comets, or maybe it was spinning in a way that kept exposing fresh, volatile patches to sunlight. Could be anything, honestly. She just told herself to check on it again after perihelion, once the comet came back out from behind the sun and they could watch it again. By then, she figured, the wild outgassing would probably settle down and the data would make sense. She never got to test that theory. When observations picked up again, everything had shifted, small things but enough to keep her up at night. It would take weeks to figure out what had really changed. On October 28th, about 36 hours before perihelion, Sarah managed to snag the last sharp astrometric image before the comet got too close to the sun. It sat at 18 degrees solar elongation, barely far enough from the sun to see, just skirting the edge before the sky washed out in glare. She caught it at twilight, that sweet spot before sunrise when the sky's still dark, but the comet isn't lost yet. The picture showed 3IATLAS as a fuzzy little blur with a faint tail. Nothing special if you didn't know what to look for, but the numbers buried in those pixels told a different story. She processed the image right away, lining up the comet's position with where it was supposed to be. It matched, right on target, no surprises. She logged the data, sent it off to the Minor Planet Center, and settled in to wait. Wait for perihelion, wait for conjunction to end. Wait until November 1st, when the sun would move out of the way and let them watch again. Those next 48 hours dragged, partly because after weeks of 18-hour days, doing nothing felt unbearable. But there was something else, too, a nagging worry she couldn't quite explain. The comet hadn't done anything dramatic, just small things, tiny deviations from the model, but they piled up. She kept telling herself it was nothing. Maybe she was just seeing patterns in noise or letting her mind run away with her. Still, the feeling wouldn't go away. On the afternoon of October 30, Hawaii time, 3IATLAS swung around the sun at about 1.4 astronomical units out. Nobody saw it, no one on Earth at least. The comet slipped behind the sun, hidden by its blinding light, out of reach for every telescope and sensor we had. Whatever happened in those critical moments, gas blasting from the surface, jets shooting out as the heat peaked, the nucleus cracking and shifting from all that stress, it all played out in total privacy. If the comet kept its own diary, maybe it made a note. For us, nothing. A day later, things shifted just enough. In theory, we could try observing again, but it wasn't easy. The comet was still too close to the sun, only about 12 degrees away, so it hovered near the edge of the sky, visible only during those thin twilight windows, right before sunrise, just after sunset. Dr. Chen gave it a shot on the evening of October 31, aiming her telescope where the comet should be. The sky was just too bright, though, and the comet too dim. All she caught was static. The first real sighting, after all, that came early on November 1, thanks to a facility in Australia with a better angle. Their first message was short. Yes, the comet was there, right where it was supposed to be, shining about as bright as expected. Dr. Chen felt a wave of relief. Whatever she'd been worrying about during the blackout, it looked like everything was fine. The comet had survived its close pass by the sun. It was acting normal. The observation campaign could pick up where it left off. But then the detailed position data started rolling in. Relief gave way to confusion, then concern, then something closer to dread. Let's jump back a bit. On October 29, as 3IATLAS moved toward perihelion, the angle between it and the sun from Earth's point of view shrank below 5 degrees. That's when optical telescopes lost track. The sun's glare was just too strong. Space-based observatories couldn't risk it either. They'd fry their sensors aiming that close. The last confirmed sighting came from a ground station in Australia, barely catching a faint smudge through the haze right before dawn. Then nothing. For 48 hours, the comet vanished, not because it was gone, but because we just couldn't look. During those 2 days, 3IATLAS hit perihelion. That's when the sun bombards a comet with its full heat, making any buried ices sublimate like crazy and shoot off jets of gas and dust. This can nudge the comet in weird, unpredictable ways. Comets are notorious for acting up near perihelion. The sudden heat cracks the surface, opens new vents, and sometimes throws the whole thing off balance. Imagine a lopsided rocket engine. Jets fire, the body wobbles, and the path gets messy. That's why nailing down a comet's future course is so tricky. But here's what's interesting. We've seen this before. Missions like Rosetta stuck with Comet 67P for years, watching every twist and outburst. We've tracked plenty of short-period comets through multiple close passes, measuring how their orbits shift because of these wild jets. The models we have now, they're solid. Not perfect, but they're built on decades of real data and can predict pretty well how much a comet's path should drift, depending on its size, makeup, spin, and how active it gets. They do the job. So when 3IATLAS popped back out from behind the sun on November 1, everyone jumped on it. Radio telescopes got the first hits, picking up its heat signature even in daylight. Optical telescopes confirmed it soon after, once the comet pulled far enough from the sun's glare. By November 2, the sharpest images were coming in again. Astronomers locked down its position, measured its speed, and stacked up the numbers against what the models had predicted before it disappeared. The numbers just didn't add up. Dr. Chen expected a bit of mismatch when she compared the comet's position after conjunction to her orbital predictions from before perihelion. It's a comet, after all. They're not just dumb rocks gliding along perfect orbits. They spit gas, lose chunks, feel uneven pushes from jets of vapor. If the comet drifted a few thousand kilometers from its predicted spot over several days, that would be totally normal. But this wasn't normal. The gaps, the residuals between where the comet actually was and where the math said it should be, weren't random at all. Not the usual scatter you get from fuzzy measurements or a wobbly atmosphere. These residuals lined up, a clear offset in one direction that just kept growing as more observations came in from different telescopes. By November 3rd, after 4 days worth of fresh data, the trend was obvious. 3IATLAS was ahead of schedule, zipping along its path faster than gravity alone would explain. And the direction of that extra speed, it practically pointed straight toward where Jupiter orbits, right at the edge of Jupiter's zone of control. She reran her orbit software, this time letting it add in a non-gravitational push, a kind of fudge factor for the thruster effect from outgassing. The program crunched the numbers and spit out the answer, about 1.2 x 10^3 astronomical units per day squared, aimed 17 degrees off the line from the sun. In everyday terms, that's a velocity change of about 10 meters per second over the 2 days around perihelion, assuming all the action happened in that window. 10 meters per second. That's barely 22 miles per hour, not even fast enough to get a speeding ticket in most cities. But for something that weighs between 10 billion and a trillion kilograms, depending on how dense it is, getting that kind of shove means moving a ridiculous amount of mass. If the comet followed normal outgassing behavior, you'd need to blow off hundreds of thousands of tons of gas to get that push. Not unheard of for a comet near the sun, but still, that's a lot. You'd expect to see some fireworks, a dramatic brightening, a wild coma, maybe some unusual gas signatures in the spectrum. Dr. Chen checked the brightness and spectral data taken right after the comet emerged from behind the sun. Sure, it was brighter than before. Makes sense, since comets usually wake up after perihelion. The coma had grown from 10,000 to 15,000 kilometers across, which suggested more gas coming off. But it wasn't the explosive kind of change you'd expect if the comet had just lost 500,000 tons of material in 2 days. The spectra showed more carbon dioxide, which fit the story, but nothing out of the ordinary. The tail, which had been faint before, now stretched 1,000,000 kilometers behind the comet, dust and gas streaming away in the sunlight. All of it looked active but not crazy. Nothing screamed anomaly. And yet the comet's path had shifted. Not by a little, by enough to blow past the error bars. This wasn't a measurement slip or a botched calculation. The shift was real. The comet had genuinely picked up speed and changed course. Dr. Chen sent her findings to her team, a mix of comet experts, orbital mechanics nerds, and observational astronomers scattered around the planet, all working together on 3IATLAS. The responses split along the usual lines. The observers, always wary of tricky data, wondered if some calibration hiccup or coordinate mismatch could explain the shift. Maybe someone used a different star catalog before and after conjunction, making it look like the comet's orbit changed when it really hadn't. But Dr. Chen had double-checked. All the positions lined up with the Gaia catalog, every single observation. The residuals were real. The dynamicists, folks who live and breathe orbital mechanics, really dug into the numbers. This is their turf. They've watched comets get nudged around by forces that have nothing to do with gravity, and they've built some pretty clever models to explain and predict that sort of thing. But when they looked at the speed and direction of 3IATLAS's acceleration, the fit was uncomfortable. The numbers were right at the edge of what their models could handle. If this comet was on the small side, say about 400 meters across, it would need to be spewing gas at a rate that's almost off the charts, pretty much at the theoretical maximum for carbon dioxide sublimating at 1.4 astronomical units from the sun. If it was bigger, closer to 5 kilometers, the numbers started to make more sense, but then you'd need a huge portion of the surface actively venting all at once. And not a small thing. The thrust would have to be really steady, not the messy, lopsided jets you usually see from tumbling comet nuclei. Dr. Marcus Acaffer over at Maryland tried to nail down what kind of gas venting could actually explain what they were seeing. He built a 3D thermal model of a spinning comet, ran the calculations for how sunlight would heat different spots, figured out the sublimation rates, and added up all the little thrusts to see if the math worked. He spent days tweaking rotation axes and shifting the active regions around. Eventually, he found a setup that could pull it off. The comet's spin tilted about 35 degrees from the orbital plane, with one hemisphere doing almost all the outgassing while it faced the sun during perihelion. Doable, sure, but specific. Honestly, more than a little lucky. He sent the group an email. I can make the model fit, but it means assuming a lot of stuff we just don't know. We never measured the rotation axis. We don't know if there are active regions on just one side. We don't know if the outgassing was steady or came in fits and starts. The model matches the data, but the data doesn't really pin it down. We're fitting elephants here, he said, classic physicist lingo for overfitting, where you can get a model to fit anything if you give yourself enough leeway, whether or not it's actually true. Dr. Chen liked that he was upfront about it. Most scientists, when you ask if their model works, will say yes if the numbers line up with reality, even if they had to make some pretty bold guesses or bend the parameters to get there. Achafer's honesty about the model's limits meant she could trust what he was saying. Sure, the acceleration could be explained by natural outgassing, but only if you were willing to accept a stack of assumptions that started to feel pretty shaky. Then the spacecraft data came in from other angles during conjunction, and suddenly everything got messier. The deviation was tiny, just 0.03 astronomical units off the predicted path, about 4.5 million kilometers. In cosmic terms, that's almost nothing. But it wasn't random. The shift wasn't some scattered, unpredictable swerve like you'd expect from uneven outgassing. It pointed in one direction, and after conjunction, the comet seemed to nudge itself onto a trajectory that aimed it right towards Jupiter's Hill sphere, the region where Jupiter's gravity takes over from the Sun. The comet sped up a little, and the direction of that acceleration lined up almost perfectly with the ideal path for a close encounter with Jupiter. That's when people really started to wonder what was going on. Look, it's not weird for comets to get pushed around by their own outgassing. Like I said, that's normal, but there are limits. The strength of the push depends on how much gas is escaping, which depends on how much sunlight hits the surface, what the comet is made of, and how the inside handles heat. For a comet the size of 3IATLAS, anywhere from 400 meters to 5 kilometers across, the standard models say the non-gravitational acceleration from perihelion outgassing should land around 10.4 astronomical units per day squared. Maybe a bit higher if it's really active, less if it's sluggish. What they actually saw was higher, not by a huge amount, but enough to put it right up against the edge of what the models say is possible. Some scientists just shrugged. Comets like to throw curveballs. Maybe 3IATLAS is just more active than we guessed. If it's packed with carbon dioxide, it could outgas more efficiently at perihelion than the usual water-heavy comets. Maybe the crust, cooked by radiation, causes weird sublimation patterns. All of that sounds reasonable. None of it breaks the laws of physics. But the real issue, the timing. If a comet goes through a big outgassing event strong enough to change its path, you'd expect to see something. Maybe a sudden spike in brightness as the coma swells. Maybe new spectral lines as different gases escape. The tail might shift, dust should pour out. There should be signs, but before conjunction, 3IATLAS looked steady. Its activity didn't ramp up as it neared the Sun. The coma was sharp, not exploding outward. No big outbursts in the days before perihelion. Basically, it looked like a normal comet, then blackout. 2 days nobody could see it. That's when it passed through the hottest zone, soaking up the most solar energy. If anything wild was going to happen, that was the time. And when it came back into view, the comet looked normal coma tail, all as expected for something just past perihelion. But its path was off. The trajectory, the exact way it moved compared to the Sun and planets, had changed. That's what makes people uneasy. If you wanted to steer a spacecraft and not get caught, you'd do it during solar conjunction. You'd wait until telescopes on Earth were blind. The Sun's glare would hide any engine emissions. You'd time your burn for maximum efficiency, maybe even use the Sun's gravity or heat if you could. When the instruments came back online, you'd look just like a comet that had naturally outgassed near perihelion. Perfect cover. I'm not saying that's what happened. I'm saying the timing makes it possible. That's the part that keeps some researchers up at night. Let's get into the details because this isn't just guesswork, it's math. Before conjunction, we knew 3IATLAS's orbit down to fine detail. Eccentricity over 1, so it's flying through the solar system, not looping around. Negative semi-major axis just passing by. Perihelion at 1.4 AU confirmed by several teams. All the orbital angles, argument of perihelion, longitude of ascending node, inclination, measured and checked. We had its position and velocity nailed down. After conjunction, things had shifted. Eccentricity dipped a bit, so its path curved more than gravity alone should allow. Its speed along the post-perihelion arc was higher than expected. The orbital plane tilted a fraction of a degree, tiny but real. Plug those into the models and ask, what kind of non-gravitational force would do that? The answer is a push about 1.2 times 10 AU per day squared at 17 degrees off the sun's radial line. That's the delta V. That's what you need to explain the gap between where it should be and where it is. Could outgassing cause that? Sure. Comet Wild 2 pulled off similar tricks during its active periods. Halley's Comet has plenty of documented deviations in that same ballpark. It happens. But here's the tricky part. The direction of the thrust matters. Comet jets usually go off in all sorts of directions as the nucleus spins and different bits heat up. Over time, the forces can net out, but the push isn't usually lined up in a neat, useful direction. It's chaotic. The acceleration vector for 3IATLAS after conjunction is strikingly clean. It points almost exactly where you'd want if you were trying to steer the comet toward Jupiter's Hill radius, not Jupiter itself, since that need a ridiculous, impossible burn, but the spot where Jupiter's gravity starts to take over. That's the sweet spot for capturing something into a stable orbit around the planet. If you were planning a mission to slip a probe into the Jovian system without burning through all your fuel, this is the path you pick. You'd swing by the sun to curve your path, tweak your course with a small burn at perihelion, and then just coast, letting gravity handle the rest. That's exactly what 3IATLAS is doing. Maybe it's just luck, maybe not, but there's more. The thermal models add another twist. Before conjunction, scientists tried to figure out how much the comet would heat up at perihelion, with a surface albedo around 0.04, so it reflects just 4% of sunlight and soaks up the rest. The predicted surface temperature at 1.4 AU from the sun was somewhere between 200 and 220 Kelvin, depending on how fast it spins and how well it holds heat. At those temperatures, water ice sticks around, but carbon dioxide ice turns straight to gas. And since James Webb's data showed the comet is rich in carbon dioxide, that meant a whole lot of outgassing was on the way. How much, though? To get the kind of non-gravitational acceleration we saw, the comet needs to throw off something like 1025 molecules of gas every second at perihelion. That translates to about 100 kilograms of material lost every second. Over the 2 days around perihelion, you're talking 17 million kilograms, or 17,000 metric tons. For a comet weighing between 1010 and 1012 kilograms, depending on what it's made of, that's 0.002 to 0.2% of its mass. Not enough to tear the thing apart, but not exactly trivial either. So, does the surface have what it takes? If the nucleus is small, around 400 meters, then the active areas have to be insanely efficient, with CO2 ice sublimating almost as fast as physically possible. If the nucleus is bigger, closer to 5 kilometers, then the numbers aren't as extreme, but you still need a good chunk of the surface venting away. Before conjunction, we saw some activity, a visible coma, a faint tail, but nothing wild. The comet didn't look like it was about to erupt. Then, after conjunction, the coma grew, not explosively, but noticeably. Follow-up spectra caught a bump in CO2 emission, matching recent sublimation. Dust production ticked up, so the tail got a little more diffuse. Basically, it all fits the story of perihelion outgassing. The weird part is how efficient it all was. The comet seems to have vented just enough gas in just the right direction at just the right time to nudge itself onto a path that's, well, perfect for targeting Jupiter's Hill sphere. That's a lot of things lining up. And then there's the rotation. All comets spin. It's just what they do, thanks to how they formed and all the bumps and outgassing they've gone through. When a spinning comet vents gas, the jets don't stay pointed. They sweep around as the nucleus tumbles, so the thrust usually wobbles around and isn't very efficient. If you want a clean, steady push, you need either the rotation axis to line up just right, so the active spots always point the right way, or you need a single big vent that keeps firing in the same direction. Both are possible, but they need special circumstances. And frustratingly, we missed the crucial window to actually watch the comet and check. What we do know, 3IATLAS spins every 8 to 12 hours, Not too fast, not too slow. If the activity was lopsided, you'd expect the thrust direction to wander over each rotation, making the push less efficient. The fact that we see a clean, directional change after conjunction means either the outgassing was weirdly symmetric, which doesn't happen often, or the active regions just happen to be in the perfect spot. Both could happen, but honestly, it's just one more lucky coincidence on top of all the others. During solar conjunction, Earth's telescopes go completely blind. There's just no way to see 3IATLAS with all that sunlight in the way. But not every set of eyes is stuck on Earth's side of the sun. Some spacecraft orbit in spots that give them a totally different view, free from our line-of-sight problems. Parker's solar probe and Stereo, for example, both had the right geometry to spot 3IATLAS when the rest of us couldn't. Let's talk about Parker first. NASA launched it in 2018, and it flies a wild elliptical orbit that brings it closer to the sun than anything we've ever built. It actually dives through the sun's corona, where it gets hotter than 1,000,000 degrees. The probe's main job is to study the solar wind, to figure out why the corona is hotter than the sun's surface, and how all those charged particles blast out into space. To survive, Parker drags along a chunky carbon heat shield that keeps its instruments nice and cool, while the outside bakes at over 1,000 degrees Celsius. It wasn't built to hunt comets, but its wide-angle cameras catch almost anything that zips by, just because they're always watching for stuff in the solar wind. In late October 2025, Parker happened to be on the far side of the sun, perfectly placed to see what Earth couldn't. If 3IATLAS crossed through its field of view around perihelion, and by all accounts, it should have, then Parker's cameras would have snapped pictures showing how bright the comet was, what it looked like, and whether anything weird was going on. Those images could help figure out if we're seeing regular comet outgassing or something stranger behind the comet's change in direction. Now, Stereo, it's the last survivor of a two-spacecraft mission NASA launched in 2006 to watch the sun from different angles. Stereo runs ahead of Earth, keeping about a 20-degree head start in its orbit. That gives it a sideways look at the Sun-Earth line, a unique perspective. Like Parker, Stereo wasn't really meant for comet spotting, but its coronagraphs. Those are the instruments that block out the sun's glare to reveal faint stuff nearby, are sensitive enough to catch comets sneaking through the inner solar system. Back in 2011, Stereo actually discovered several Kreutz Group comets, those daredevils that skim right past the sun before breaking up. During the conjunction, Stereo's cameras were working, and its orbit lined up just right. So 3IATLAS should have been visible at least at the edges of its view. Here, where things get messy, and honestly, it gets more confusing the deeper you dig. The data from these spacecraft is out there for anyone. NASA posts it all online, raw and processed, so anybody with a decent internet connection can download the images. Space science, at least in theory, is all about radical transparency. Public money pays for the missions, so the results go straight to the public. Anyone, pros, amateurs, skeptics, can go poke through the evidence and draw their own conclusions. That openness is a big deal. It keeps science honest and helps guard against mistakes or hidden bias. But in real life, this kind of transparency isn't as simple as it sounds. The data isn't a bunch of pretty pictures you can scroll through. It's mountains of raw numbers, detector readings, cosmic ray hits, weird distortions. Turning that into something you can actually look at takes a whole chain of software, calibration files, and deep knowledge about the instruments. The mission teams handle most of this, releasing cleaned-up images that are easier to use. But every step of that cleanup involves choices. How to subtract background noise, how much to filter out, what to highlight or ignore. These aren't sinister moves, they're just technical calls. Still, the decisions shape what ends up in the final images, and sometimes, what quietly disappears. During the conjunction, a handful of independent researchers and amateur astronomers took matters into their own hands with 3IATLAS. They didn't just accept the standard processed images. Instead, they dove headfirst into the raw data, downloading mountains of unfiltered frames from Parker and Stereo. Then they tried their own hand at reducing the data, leaning on open-source tools and tutorials the mission teams had put out there. This wasn't about mistrust, at least not at first. It was pure curiosity. Maybe, just maybe, they'd find something the official pipeline missed. That's a classic move in astronomy. Amateurs have a real history of stumbling across important stuff by poking around in old data. Take Hannes Voorwerp, a Dutch schoolteacher digging through Galaxy Zoo images, spots a bizarre green blob near a distant galaxy. Or comet ISON. Amateurs noticed its brightening before perihelion because they watched it more often than the pros. Sometimes not being an expert helps. You don't have the same blind spots. So, what did they find with 3IATLAS? Well, really it was more about what they didn't find, and that kicked off a lively debate online, forums, mailing lists, all the places where technical arguments happen in the shadows of the main journals. In Stereoway's coronagraph images from October 29th and 30th, 3IATLAS showed up as a faint streak, more or less where the model said it should be. But it was dim, much dimmer than you'd expect for a comet supposedly in the middle of a big outgassing event near the sun. Some folks argued that meant the comet wasn't as active as everyone thought, which throws a wrench in the usual explanations for its post-conjunction orbit change. If there's not much gas blowing off, there shouldn't be much thrust, so why did the orbit shift the way it did? That's a real puzzle. Others pushed back. They pointed out that stereo wasn't built to measure comet brightness precisely, and any dimness could just be due to how the images get processed, background subtraction, weird saturation from bright solar features, that sort of thing. Coronagraphs, after all, block out the sun with an occulting bar to fake an eclipse, but that creates a bright halo from scattered light and diffraction. If 3IATLAS ended up too close to that halo, the background could easily drown out the comet's signal, making it look fainter than it was. Both sides have a point. Both explanations make sense, but without digging into the calibration data, stuff usually only mission insiders have, nobody can settle the argument for sure. Now, the Parker Solar Probe images. That's where things got even spicier. The mission team released process pictures covering the spot where 3IATLAS was supposed to be during perihelion based on earlier orbit calculations. But the comet doesn't leap out at you. It's not obvious, at least not to the casual eye. Some independents say they've found a faint something in the raw data, right where 3IATLAS should be. They've posted screenshots, circled blurry smudges, drawn arrows. Depending on who you ask, it's either the comet or just noise. So why isn't it clearer? Honestly, the simplest answer is the most likely. The comet was just too faint. Its activity probably wasn't enough to make it stand out against the sun's glare and Parker's own instrument noise. Those imagers were built to capture solar wind, not chase after dim comets, and they might not be able to handle both in the same shot. If the background's bright and the comet's a ghost, it gets lost. Or maybe nobody's tuned the data processing for comets at all. Because, let's face it, that's not Parker's job. The science teams are swamped with solar wind analysis, tracking coronal mass ejections, mapping magnetic fields. They're not combing through every frame for surprise comets unless somebody really pushes for it. And even then, time and resources are tight. Every hour spent hunting comets is an hour taken from the main mission. There are always trade-offs, and not everything makes the cut. There's another theory people mention quietly, usually behind closed doors or hidden away in obscure forum threads by folks who claim to know more than they let on. What if the comet wasn't pushed to the front in the official data not because of some dramatic cover-up, but because what they actually saw was unclear, open to interpretation? If you hand that kind of ambiguous data to the public without context, rumors and wild guesses spread faster than the facts. Space agencies aren't exactly known for taking risks. They've learned the hard way that sharing early, unreviewed results only leads to headlines that spiral out of control and confusion that sticks around long after. So they wait. They'll sit on data until they're sure what it means, until they can tell a story that holds up under tough questions. But that kind of caution leaves empty spaces, and those gaps don't stay empty for long. When the official reports go quiet and the raw numbers never see daylight, people start to wonder what's being kept from them. Maybe nothing's actually being hidden. Maybe it's just scientists being careful, doing what they always do. Doesn't matter. The silence feels the same. It starts to look like someone is managing the truth instead of just sharing it. One name keeps popping up if you dig around conversations about Parker's 3IATLAS observations, usually whispered or tucked away where only the dedicated will find it. Dr. Amanda Reyes. She's a planetary scientist at Johns Hopkins Applied Physics Lab, the place that runs Parker's solar probe's operations and data crunching. She's kind of a big deal in the world of dusty plasmas, the weird dance of tiny charged particles out in space, especially around comets and ring systems. She's been in the mix since Parker's earliest days, published a ton, and if anyone's in charge of making sense of surprise comet data from this mission, it's her or someone she works with. In mid-November, right after 3IATLAS came out of conjunction and the world started watching it again, Dr. Reyes gave a talk at a small workshop focused on interstellar objects. It was a virtual meeting, invite-only, mostly just scientists in the field sharing early ideas, stuff that isn't ready for the spotlight yet. These kinds of workshops are important. They're where half-finished thoughts and I'm not sure yet moments are allowed, where you can actually admit you don't have all the answers and get some feedback, instead of pretending everything's polished and final. Her talk was called Thermal and Morphological Observations of 3IATLAS During Perihelion, Preliminary Analysis from Parker's Solar Probe. Like most online events, they recorded it and put it up for attendees to watch, at least for a little while. Then, just days later, the video disappeared from the workshop site. The official word was technical issues, audio problems, bad sync, that sort of thing, made the recording too hard to follow. But a few people had already watched it, and at least 2 took detailed notes. Those notes ended up floating around, first through email, then in bits and pieces on research forums. According to what people shared, Dr. Reyes showed early analysis from Parker's Wide Field Imager, covering observations from October 29 to 31. She talked about spotting what looked like 3IATLAS in several frames, matching up with where the comet was supposed to be. The comet itself came through as a faint blip, dim, but active enough for that distance from the sun. Nothing dramatic, but definitely there, standing out above the background after some careful work. She shifted gears and brought up something that didn't fit the usual story. The comet's infrared brightness temperature, measured across Parker's different detector bands, came in higher than anyone expected if you just factored in sunlight. Not by a huge margin, maybe 20 or 30 Kelvin over the standard thermal model, but enough to matter. That extra heat could mean a few things. Maybe the comet's surface is darker than we thought, soaking up more sunlight. Maybe the way the surface holds and releases heat is different, so it heats up faster or cools down slower than models predict. Or maybe, just maybe, something inside the comet is producing heat, though what nobody could say. Tidal forces from gravity. No way, not at that distance from the sun. Radioactive decay. Sure, that's always happening, but it barely adds any warmth. Definitely not enough to explain what they saw. She didn't stop there. She also pointed out some brief flashes, transient brightening events, that showed up in just a handful of frames. Each one lasted only seconds. These little bursts could mean all sorts of things. Maybe tiny meteoroids or dust grains slammed into the comet and vaporized, causing a quick spike in brightness. Or maybe pockets of gas under the surface broke through, erupting like miniature geysers. Or maybe the whole thing was just a glitch, cosmic rays hitting the detector at just the wrong time, or some other technical hiccup. Hard to tell, honestly. Without more data or someone else's confirmation, it was impossible to sort out what really happened. Dr. Reyes wrapped up by leaning into the uncertainty. She made it clear. These results were early, the data wasn't perfect, and every possible explanation had to be checked before anyone could draw real conclusions. She called for more observations, for other teams to pitch in spacecraft, ground telescopes, whatever it took to clear up the picture. She wasn't making wild claims or hyping up the mystery. She just laid out the facts and asked the scientific community for help. So what happened to the recording? The official story was technical issues, which honestly happens all the time with virtual meetings. But the timing felt odd. Why take it down only after people had already watched it? If the video quality was bad, why post it in the first place? It's easy to see why some folks got suspicious. Maybe someone at Johns Hopkins or NASA worried that early, messy findings would get twisted into clickbait headlines and decided to quietly pull the plug. Maybe they wanted to keep the narrative under tighter control, wait for peer-reviewed papers and official statements instead of letting workshop chatter set the tone. Whatever the real reason, the outcome was predictable. Pulling the video just made people think there was something to hide, even if it was all pretty routine behind the scenes. Gaps in the story always invite speculation, and once rumors start, they're tough to stamp out, no matter how much data you release later. In January 2026, Dr. Reyes and her team put out a preprint on RZIV, laying out Parker's observations of 3IATLAS in full detail. The results matched what she'd shared at the workshop, slightly warmer than expected, some quick flashes, lots of caveats and calls for further research. They concluded the comet was probably just a little more active near perihelion, nothing too wild, but they couldn't rule out other explanations. It was a solid paper, thorough, honest about the limits of the data. But by then, 3 months after the fact, the story had already taken on a life of its own. For some, the missing video was proof of a cover-up. The cautious wording in the paper, proof the scientists were holding back. Once those ideas took root, it didn't matter how much evidence came out after. The suspicion stuck. Dr. Reyes turned down every interview request. She answered through a Johns Hopkins media officer, short, polite, and to the point. The Parker Solar Probe observations of 3IATLAS are being analyzed alongside data from other missions and ground-based facilities. We're preparing a detailed, multi-wavelength study that will submit to a peer-reviewed journal in early 2026. Until then, I can't comment beyond what's in our recent preprint. That's standard procedure in science. Totally appropriate. Still, if you're trying to figure out what really happened during those 48 hours, it tells you nothing. Let's zoom out and talk about the classified data side of things, because that's where things get messy. The US runs a web of surveillance satellites built to catch missile launches, nuclear blasts, and anything else that lights up in the infrared. These satellites, part of the space-based infrared system and newer versions, are always watching Earth and the area around it. They don't aim out at the rest of the solar system, but their broad sensors sometimes pick up unexpected stuff. Astronomical flashes, meteors burning up, even supernovae far away. Most of their data stays locked up, but sometimes, if it's useful for science, a bit gets released. Could these satellites have caught 3IATLAS during its closest approach to the Sun? The geometry works out, at least in theory. If the comet was bright enough and crossed a satellite's field of view, the sensors would have seen it. Would that have shown anything odd? It's possible. A sudden bright flash or flare, something more than the usual outgassing, would stand out in the infrared. But honestly, we'll never know. Even if that data exists, it's buried in classified files, and the chance of it being released just to study an interstellar comet is basically zero. National security always wins over scientific curiosity. That said, scientists do have sneaky ways to hunt for classified observations. Researchers with security clearances sometimes drop hints they can't spell out. You'll spot phrases like observations from assets I cannot specify, or alternative data sources corroborate these findings sprinkled in papers, code for we used classified data. With 3IATLAS, though, I haven't seen any of that. Still, not seeing hints doesn't mean the data isn't there. Maybe no one with access is willing to risk their clearance by leaking anything. Now, about the comet's acceleration. If you look at it from an engineering perspective, things get interesting. Let's say, just for argument's sake, that 3IATLAS used some kind of propulsion during the blackout. What kind of engine would it take to pull off the velocity change people observed? The numbers are smaller than you'd think. A change of about 10 meters per second over 2 days, right around perihelion. For a spacecraft with efficient engines, that's a walk in the park. A few kilos of propellant for a medium probe. Even for something bigger, the fuel needed wouldn't be huge. But here's the problem. Regular rocket engines make exhaust you can see. Hot gas, charged particles, bright flares in all sorts of wavelengths. If 3IATLAS fired up a chemical or ion engine, even for a moment, telescopes would have spotted a sudden brightness spike or odd spectrum. Unless, of course, the burn happened when nobody was watching. Or maybe the propulsion wasn't anything ordinary. Maybe it didn't leave a noticeable trace. Electric engines, like ion drives, give off almost invisible exhaust, mostly in the ultraviolet. If you're not hunting for that, it's easy to miss. Go weirder, say nuclear thermal or solar thermal engines. They could be built to hide their tracks, using propellants that barely show up in visible light. And if you really wanted to hide an engine burn, you could just vent some stored gases at the same time. The resulting cloud of gas and dust would cover up anything suspicious, making artificial thrust look just like natural comet activity. Let's be honest, this is all guesswork. There's no sign that 3IATLAS has engines, nothing artificial in its structure, no weird signals, no unexplained emissions. Still, the fact that this idea even makes sense on paper, that the math works, that the timing lines up, it keeps the question alive. Because once you show that something could be artificial and could pass for natural, you can't really prove it is. You're stuck with probabilities and Occam's razor, hoping the simplest, natural explanation is the right one. But what if it's not? What if we're looking at something built to be mistaken for a comet? That's the thought that keeps a handful of researchers up at night, the ones who have stared at the data a bit too long. If a really advanced civilization wanted to slip probes into other star systems without tipping anyone off, this is exactly what they'd do. Build ships that look like comets, ice-caked messy, loaded with volatiles that start evaporating as soon as they get close to the sun. Anything important is buried deep, wrapped in meters of ice and frozen gas. The engines only kick in when the sun's close, using the heat and glare as cover. From the outside, you'd never know. It's just another comet until it is. This isn't some brand new idea. Astrobiologists and SETI folks have talked about camouflaged probes or stealth reconnaissance for years. Logic's simple. If you're exploring a galaxy where you might not be welcome, you don't show up blasting radio signals and flying obvious spaceships. You blend in, you use what's already there. Asteroids and comets are everywhere. Nobody pays attention. It's the perfect disguise for anything trying to sneak by. So does that mean 3IATLAS is a camouflaged probe? No, absolutely not. There's just no real evidence for it. But you can't dismiss the possibility just because it looks natural. That sliver of doubt sticks around. It's enough to keep people watching, and honestly enough to make some scientists uneasy as we wait for this thing to reach Jupiter's Hill sphere soon. If it is a probe, if it's here for a reason, it won't act when we're ready. It'll move when the timing's right, when Jupiter's gravity gives it the boost it needs, when nobody's paying close attention. Now, let's talk about how the community's handling all this, because the reaction to the latest data has been pretty telling. The mainstream science crowd, NASA, ESA, the big universities, has played it safe and steady. Their take, 3IATLAS is just an interstellar comet. The trajectory changes match what you'd expect from outgassing near the sun. Sure, it's got some weird quirks, but nothing that demands an artificial explanation. They point to the JWST data showing regular comet stuff, the coma and tail, the lack of any odd signals. That burst of acceleration during solar conjunction. Just bad timing, not suspicious. Comets always get active near perihelion. But the skeptics, scattered across online forums, independent research circles, and a few credentialed scientists willing to talk off the record, aren't buying it. They're not claiming 3IATLAS is definitely artificial, but they think the official story glosses over too much. Take the polarimetric signature. No known comet matches it. Or the carbon dioxide levels, hinting at a birthplace way outside our solar system's usual. Or that post-conjunction trajectory shift that seems a little too perfect for targeting Jupiter. Add in the missing or muddled spacecraft observations during the blackout. Each weird detail might have an explanation, they say, but stack them all together, and it feels like more than just a coincidence. People keep tossing around this phrase, consilience of inductions. Basically, it's a fancy way to say that when lots of different bits of evidence all seem to point in the same direction, you start to take the conclusion seriously, even if every single piece on its own is flimsy. With 3IATLAS, that's the core of the argument. Sure, maybe no one thing proves it's artificial, but when you add up the weird signals, the odd timing, the strange path, and all the missing data, it all starts to pull together. It doesn't scream aliens, but it definitely suggests something that doesn't fit the usual, just a comet story. Maybe it's some kind of engineered interstellar traveler that we just don't get yet. Or maybe it's a natural object that just happens to act in a way that feels a little too intentional. Then you get the fringe crowd, the conspiracy folks, the UFO obsessives, who pounce on 3IATLAS as their smoking gun for alien visitors. They pass around blurry images claiming to spot geometric shapes in the comet's coma. They regurgitate already debunked rumors about mysterious radio signals. Some even spin wild stories about government cover-ups and missing data. Honestly, they just make things messier. Legitimate questions start to look ridiculous by association, and real scientists end up worried about being branded as crackpots. So when someone with credentials wants to ask about the comet's odd post-conjunction path, they risk being lumped in with the tinfoil hat crowd. That shuts down honest conversation and pushes doubt into the background. This whole situation, the tug-of-war between total certainty and wild speculation, leaves almost no space for honest uncertainty. You're supposed to pick a side. It's nothing, just a comet or aliens for sure. Admitting we don't know yet doesn't really fit, but that's exactly where real science lives, in the gray area and the willingness to say, the data's a mess, we need more. Out in the world, though, nobody rewards ambiguity. People want confidence, even if it's fake. So the scientists who aren't sure about 3IATLAS tend to play it safe in public, sticking to the standard line, even if privately they admit the whole thing feels off. I've talked to a few researchers behind the scenes, people who have seen the full data sets, spent months poring over the numbers. What they tell me is a lot more complicated than what you hear at press conferences. One astronomer at a big observatory put it like this: the outgassing theory fits the math. But you have to assume the comet has a very particular interior structure and just the right spin. Is that possible? Yeah. Is it the only answer? No, but it's the safe answer. It doesn't force us to rethink everything or consider the weird stuff, so that's what we use. Another scientist, who's knee-deep in the spectroscopic data, told me something else. The chemical makeup is weird, no doubt. The carbon dioxide levels are nothing like what you find in our solar system's comets. But you'd expect that from an interstellar object. It formed somewhere else under different conditions. The odd chemistry isn't alarming, just interesting. What really gets me is the trajectory, the timing at perihelion, the blackout during conjunction. It all lines up a little too neatly, and I don't buy coincidences. Still, I don't have proof of anything else, so I keep quiet and keep working. A third contact, someone with access to satellite data they wouldn't pin down, was even more cryptic. There's stuff people haven't seen. I can't tell you what's on it, but I can tell you it doesn't clear anything up. It just raises more questions. And until someone can answer those, the data stays locked up. So what are we supposed to do with all these half-whispered comments? Are they signs of some big cover-up, or just the normal messiness of science, where you keep things close until you're sure? Honestly, it's probably the second one. But either way, the result feels the same. There's this nagging sense that we're not getting the whole picture, that the official story has been scrubbed clean, stripped of the confusion and loose ends that always come with real research. So what comes next? The story isn't finished, not by a long shot. Right now, 3IATLAS is heading out, pulling away from the sun on a hyperbolic path. Over the next few months, it'll keep getting dimmer as it moves farther out and loses steam. By the middle of 2026, unless you're working with a monster of a telescope, you won't see it. By the end of that year, it'll just disappear, swallowed by the emptiness between the planets. Before that happens, astronomers have a small window to squeeze as much information as they can, refine its orbit, check for weirdness, try to catch anything that tips the scales. The big thing to watch for is when it gets close to Jupiter's Hill sphere. That's supposed to happen in late 2026 or maybe early 2027, depending on exactly where it's headed. If there's any truth to the Sentinel idea, that's when you'd expect something dramatic, maybe a sudden flare, the comet breaking into pieces, or a bunch of smaller objects peeling off and moving on their own. Ground-based observers will be watching, but it's going to be tough. The comet will be faint and hard to track. Space telescopes could catch something if they're pointed the right way at the right time. But if Jupiter happens to be behind the Sun from our point of view, or the angles aren't right, we might miss the whole show. And what if nothing happens? If 3IATLAS just keeps drifting away, growing fainter, never putting on a show, then the mystery fizzles out. That weird post-conjunction blip in its path just gets chalked up as an odd but explainable burst of outgassing near the Sun. The anomalies become footnotes, maybe referenced in a few research papers as another example of how strange interstellar visitors can be. The question of what happened during those 48 missing hours. It'll turn into some obscure internet debate, mostly forgotten by everyone else. But if something does happen, if the comet breaks in a way that's not random, if chunks split off and start orbiting Jupiter, or if any of these wild theories actually play out in a way we can see, then we're facing something big. Suddenly, it's not just a comet. That would change everything. The search for extraterrestrial intelligence, it gets a whole new urgency. Governments would need to rethink how they watch the skies. Every future interstellar object would become a high-priority target, not just for scientists, but for anyone thinking about security and strategy. And there's a bigger picture. Right now, people are taking the idea of non-human intelligence more seriously than ever. The Pentagon talks openly about strange things in the sky. SETI and technosignature research are getting more money and attention. Astrobiology is starting to shift from if we'll find life to when. We're primed to look at strange data and see meaning, where earlier generations might have shrugged and moved on. That's the context for 3IATLAS. It's not just a comet. It's a kind of Rorschach test, something onto which we project our hopes, our fears, our questions about whether we're alone. For some, it's a hint that we're not, that someone out there is sending messengers across the vast dark. For others, it's a reminder that we're exposed, unable to control what drifts through our part of space. And for scientists, it's a challenge, a test of how you do good science when the evidence is murky and everyone's watching. Those missing 48 hours sum it all up. A literal blind spot, a gap in our knowledge that leaves the door wide open. Did 3IATLAS just burp out some gas and nudge itself onto a new path? Did it crack or vent in some random way? Or did something deliberate happen, a maneuver timed for the one moment when nobody could see? We're left staring into the dark, waiting for answers. We probably won't ever get a clear answer. That's just how it goes. Some mysteries stay mysterious no matter how much we poke at them. We end up with best guesses dressed up as certainty, but deep down there's always a bit of doubt. Most scientists say 3IATLAS is just a regular comet. The numbers mostly add up. Still, those weird details, the outliers, the timing keep nagging at us. They don't fit the story we want to tell. And you know what? Maybe that's fine. Maybe it's healthy to admit we don't know everything, especially when we run into something that doesn't quite fit our models but isn't outright impossible either. Maybe the real lesson from 3IATLAS isn't about what the object is, but what it shows us about the limits of what we can see, the holes in our coverage, the things that slip by when we're not paying attention. Think about it. If something or someone wanted to move through the solar system without getting spotted, if some advanced intelligence wanted to stash something near Jupiter and not tip off us Earthlings, they'd start by figuring out where we can't look. They study our telescopes, our satellites, map out our blind spots, and they'd wait for their moment. Solar conjunction is the obvious one, our biggest, most predictable blind spot. It's unavoidable, and it just happens to be the perfect time for the kind of weird trajectory shift we saw. Maybe that sounds paranoid, or maybe it's just how humans work. We notice patterns, we're built to spot stuff that's a little off. It's the same instinct that kept our ancestors alive, the rustle in the grass that could be wind or something hungry, the shape in the distance that might be a rock or might be something else. 3IATLAS sets off that instinct. Looks like a comet at first glance, but the closer you look, the more things don't quite line up. Honestly, I don't know what 3IATLAS is. Nobody does, not for sure. The experts have their theories and favorites, but even they'll tell you the data's got holes. We missed nearly 2 days of observations, right when it mattered most. That blackout will always leave room for questions, for alternative theories, for the nagging thought that maybe we saw something historic and didn't realize it. Here, what I do know. The next time something like this shows up, astronomers won't get caught off guard. They'll double up on observations, use more instruments, cover angles they used to ignore. They'll push for more funding to plug the gaps and keep watch even when the sun gets in the way. Whether 3IATLAS was just a weird comet or not, it exposed a vulnerability. We missed our chance to watch during the most important window. That kind of miss just isn't acceptable anymore. Now people are talking about launching CubeSats to watch from the side during solar conjunction, so we're not blind when Earth-based telescopes can't see. There's talk of borrowing military satellites for astronomy, at least when something interesting passes through. Some even want to build missions just to chase down interstellar visitors like this one, to get up-close data and cut out the guesswork. All good plans. We need them. But they're coming after the fact, because we realized too late that we missed something. That's the tough part. The best time to build this stuff was before 3IATLAS, not after. We always seem to be one step behind, scrambling to study things we didn't expect with tools we don't quite have. That's the story of humanity, really. Always trying to keep up with a universe that doesn't care if we understand it or not. So what do you take from all this? Honestly, I don't think there's a neat little lesson here. If you're looking for certainty, I can't give it to you. The official story says 3IATLAS is just an interstellar comet, venting gas as it swings close to the sun, moving a bit oddly, but nothing outside the rules of comet physics. That's probably true. It fits the data, and it doesn't ask us to twist ourselves into knots. But it's not the only way to look at things. There are other ideas, more out there, sure, but not impossible. They just make us uneasy. Uneasy because they shake up what we think we know. That we're alone. That the galaxy is this big, empty place with nothing but rocks and dust, where intelligent life is rare and nobody's calling. It's uncomfortable even to imagine we might be watched, studied by something that doesn't care to be seen. Or that we're just missing things flying past us, blind to what's right in front of us in the dark. Those 48 hours when 3IATLAS slipped out of sight, maybe they were nothing. Just a comet doing comet stuff, venting gas, passing through the solar system spotlight. Or maybe that was the moment something strange happened, something we couldn't spot because we didn't know what to look for. Maybe we saw what we expected and nothing more because we had no frame of reference for anything else. Maybe it was camouflage by accident or by design. We'll keep watching. We'll keep digging into the data. The next interstellar visitor is coming, count on it, and next time we'll be sharper. More telescopes, more coverage, fewer blind spots. We'll ask tougher questions and push for better answers. But we'll also remember 3IATLAS and what it taught us. Sometimes, the most important stuff happens in the gaps, in those moments when nobody's looking. That's the real gift of this story. A little humility, a reminder that the universe keeps its secrets, and sometimes all we get is a glimpse. The story isn't over. It's just in a holding pattern. In the months to come, as 3IATLAS heads for Jupiter and fades from view, we'll find out if the weirdness stacks up or fades away. Maybe this comet becomes just another line in a table, or maybe it's the start of something no one saw coming. And those 2 missing days in October when the world blinked and something shifted in the dark will stay with us. That gap is ours to fill with data, with theories, with stories, but never with full certainty. That's what we're left with. Not answers, but better questions. Not a conclusion, but a deeper itch to know more. And maybe, just maybe, a nagging feeling that we're not as alone as we thought. The silence of space isn't as empty as it seems. Somewhere out there, other eyes are open. Other minds are doing the math. Other travelers are on their way. And here on Earth, we're building the tools to watch the sky like never before. Every year the gear gets better. More surveys, sharper cameras, smarter algorithms. The Vera Rubin Observatory in Chile will scan the whole sky every few nights once it's up and running in 2025, pulling in so much data that finding moving objects becomes a job for software, not just human eyes. Soon, the Nancy Grace Roman Space Telescope will launch, with infrared eyes that'll spot cold, faint things regular telescopes miss. Ground telescopes are getting upgrades too, with adaptive optics that clean up the blur from Earth's atmosphere, making images almost as crisp as what we get from space at a fraction of the price. With all this tech, we're not just hopping to find more interstellar visitors. We will. 3IATLAS won't be special for long. In the next decade, astronomers expect to catalog dozens, maybe hundreds, of objects dropping in from the space between stars. Every one of them is a clue, a piece of the puzzle about how planets form, how solar systems toss out their leftovers, what kind of stuff builds up out there, far from home. Each new visitor brings us closer to the answers, and as always, a few more questions. Every time astronomers look deeper into the sky, they find more things that just don't line up with what they expect. Strange objects that act in ways natural physics has trouble explaining. Odd flight paths that seem too lucky, too perfectly timed, almost as if someone planned them. If 3IATLAS is just the first in a long line of these weird visitors, if its 2-day blackout and last-minute course correction turn out to be the start of a pattern, the next decade is going to push astronomy into territory it's always tried to avoid. It'll have to ask real questions about intention, about design, about whether at least some of the stuff we're cataloging out there isn't natural at all. That idea is scary and thrilling at the same time. Scary because it blows up the comforting belief that we're alone in the universe, a belief humans have leaned on for centuries. There's a kind of safety in thinking we're just talking to ourselves out here. No one to judge us, threaten us, or even ignore us. It's a small comfort, but a real one. On the other hand, the excitement comes from flipping that idea on its head. Imagine discovering we're not alone. Imagine finding out intelligence is common enough that we spot the evidence in our own solar system and in our own lifetimes. That would change everything: philosophy, religion, politics, all of it. The way we see ourselves would never be the same. Right now, 3IATLAS sits right at the center of all these feelings. Odds are it's natural. That's what the evidence says, sort of. Not strongly, not definitely, but enough that most scientists lean that way. But probably is definitely, and that little gap is full of possibilities. Maybe, just maybe, we witnessed something huge and didn't realize it. Maybe, while the comet was hidden behind the sun for those 48 hours, something happened. An interstellar visitor finishing a journey that started before humans ever existed. Maybe what came out from behind the sun wasn't exactly what went in. If that's the case, if 3IATLAS is or was a probe, or a ship, or something dropping off smaller payloads near Jupiter, well, we'll find out soon enough. Astronomers keep a close eye on Jupiter's oddball moons, the little captured rocks in messy orbits around the giant planet. If anything new turns up, if they spot a moonlet that looks just like 3IATLAS and it's sitting in an orbit that doesn't make sense naturally, things will get serious. Talk will shift from wild theories to real scientific investigation. People will start planning missions, aiming spacecraft at the object to get a closer look. Old contact protocols, those dusty files left over from the SETI days, will get pulled out and updated, even though no one ever really expected to use them. Or maybe nothing dramatic will happen at all. Maybe 3IATLAS just drifts away, leaving the solar system with only a gentle nudge from Jupiter's gravity. Eventually, it'll fade from view, getting too dim for even the largest telescopes. The mystery of its 2-day disappearance will become a footnote, something for academics to argue over now and then, but never really solve because the crucial data just isn't there. Next time, astronomers will be ready. They'll watch more carefully, build in backups, and close those gaps in coverage. They'll get better little by little. And maybe someday, they'll catch an object doing something so obviously artificial that nobody can explain it away. But until then, we live with the unknown. The data points in a bunch of directions. The explanations work on paper, but they force us to swallow some uncomfortable ideas. Our tools are good, but they're not perfect. We miss things when the sun gets in the way, when equipment fails, when we just can't cover every wavelength or see every detail from so far away. That's where the mysteries linger. In those gaps, anything can happen. That's where nature and artifice blur, and sometimes crossing that line goes unnoticed. Those 48 hours when 3IATLAS slipped out of sight, it's like cramming every gap in our understanding into one intense, loaded moment. The curtain dropped. Something happened out there and we missed it. That time's gone for good. We can look at what came before, we can study what came after, but that middle part, it's just not coming back. No matter how much we want it, we can't turn back the clock or squeeze new data out of thin air. We're stuck with the uncertainty, and honestly, that's what gives this whole story its bite. It's fascinating and maddening at the same time, because science just can't reach into that blank space and pull out answers. Maybe that's how it should be. Mysteries aren't here to be solved in an afternoon. Sometimes they're meant to stick around to remind us that not everything has a tidy explanation. The universe isn't interested in handing us clarity. It's not bothered about whether we figure things out. Things orbit, things drift, comets shed gas, and whether that's all just physics or something more deliberate doesn't matter to space itself. It matters to us, the people watching, trying to piece together meaning from a handful of photons, some measurements, and a whole lot of unknowns. So when something new shows up, we need to be ready to really see it. Every kind of it. The ones that look like comets, the ones that use the sun to hide, the ones that pull off their tricks in those exact hours when we're not looking, right in the middle of our blind spots. That's where the real possibilities hide, and we're still learning how to imagine them.